We're going to continue working on sketching functions by adding this extra piece. So if you look at this equation here, y equals 5 minus 2x, up until that point, I'm just going to jot that down, that is just a line. And that line is in the b minus mx format that we've been sketching for quite a while. And you're going to add to that line an extra piece, the x value squared. Now, you've never had a piece with an x squared on it, so that's going to do something to these graphs. We'll just hang on to that for a minute. But to start, I'm just going to sketch this much, y equals 5 minus 2x. So when we started with lines, we even just looked at this first number, said where are all the places where y is 5? So I go on to my axis here and I count up 1, 2, 3, 4, 5 squares. That's where y equals 5. And I just dashed across here, like so. I'm just going to acknowledge that is y equals 5. From that, we started taking off 2 for every x value. So if I go to a particular place like 1, 2, 3, 4, 5, 6, I have to take 2 off 6 times when x is 6. So 1, 2. That's where x is 6. Take 2 off once, off twice, off 3 times, off 4 times, off 5 times, off 6 times. Pick a different x value, like 2. I have to take 2 off of this line twice when x is 2. So take it off once, take it off twice. X value of 4, start at 5 and take off 2 4 times when x is 4. 2, 3, 4. Take it off once, take it off twice, take it off 3 times, take it off 4 times. And what that ended up generating was a line where you started at 5 on the y-axis and you dropped 2 squares for every 1 you stepped to the right. So if I try and continue the pattern that way, 2 down, take a step to the right, 2 down to the right, 2 down to the right, right, 2 down to the right, 2 down to the right, and trace the pattern back up this way, and end up with this line here. That line is y equals 5 minus 2x. Now we're going to add this thing to it. So the same way that I took 5 and used it as my count line to make this slanted one, I'm going to use the slanted one as my count line to add on the x squareds. Now I'm just going to work a little ahead here and make a list of what those x squareds are. When I'm here, the x value is 0. So x squared means take the x value and multiply it by itself. So example, if the x value is 4, then x squared would be 4 times 4, which is 16. Okay, so here 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. And at that point, these numbers are going to be too big to fit on a graph anyway, so I'm just going to stop. If you go the other way, negative 1 times negative 1 is positive 1. 1 times 1 is 1, and a negative times a negative is a positive. Negative 2 times 2 is 4. Negative 3 times 3 is 9. And then 16, 25. It's this same sequence of numbers. So you might want to put that down on a study sheet, your list of perfect squares. Zero, 1, 2, nope. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 25, 36, 49, etc. So I'm going to take these numbers and I'm going to count up. Because it says plus, I'm going to count up these perfect square values from the blue line. So from here, I'm supposed to go up 0, so I don't go anywhere. From here, I'm supposed to go up 1, so I would be here. This one, I'm supposed to go up 4. 1, 2, 3, 4, so I'm here. From here, I should go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. From here, I should go up 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16 would be up here somewhere. And notice I'm off the grid now. So I'm going to go that way instead. From here, I should be adding none. From here, I should be adding 1. From here, I should be adding 4. Puts me here. And if I were to connect all of those dots, get a shape like that. You're going to be drawing a lot of these. This shape has a name. This is called a parabola. And you might have heard that word like parabolic. You can buy parabolic microphones. Parabolic microphones dish around it is shaped like this, and they're exceptional at reflecting sound right to a focal point where it can be picked up. So you can hear things very clearly from a long distance. But that's not what we're doing here. We're just doing the math. So that shape's called a parabola, and it has a very particular spot here that's important, this lowest point. The name for that is the vertex. So we're going to be drawing a bunch of these parabolas. We're going to start writing them when they're in standard form, right? When they have a number with an x and a number with an x squared. We're going to do a couple more examples. And eventually, we'll be manipulating this to make vertex form, and then we'll be sketching from different forms, doing all sorts of stuff, so that you can get used to how to manipulate functions for when you start manipulating all the other functions like sines and exponentials and logarithms, etc. So I'm going to clean this off, and we'll try another example of sketching from standard form. We're going to try this one. Sketch y equals -3 minus 4 times the x value plus the x value squared. So I'm going to start with y equals -3. So I find that place, -3, and I just dash it across. It's going to acknowledge that's y equals -3. To that, now I'm going to try and sketch y equals -3 minus 4x. So I go from this count line and drop 4 for every new x value. So new x value, drop 4. New x value, drop 4. New x value, drop 4. So that line goes down like so. Continue the pattern this way. There it is. All right. Now to finish, I'm going to sketch y equals -3 minus 4x plus x squared. Now, adding x squareds, I need to know these numbers or have them written down somewhere. So starting at this place, right, this seems to be always where we start from, I should be going up 0. Up because it's positive, 0 because that's my perfect square. So from here up 0, I'd be there. Take a step over, I'm on my next perfect square. From here, I should be up 1. Go to the next dot. I should go up 4 from there because that's my next x squared value. 1, 2, 3, 4. Next x value, I should be up 9 because that's my next perfect square in the sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, I missed here. 1, 2, 3. 1, 2, 3, 4. That should be there. Next sequence would be 16. Now I can't see where that lands. But do you notice that I've come around the corner? So this function is already on its way back up. And if you keep in mind, the parabolas look like this. They have a lowest point we call the vertex, and they are perfectly symmetrical. So I don't need this line anymore once I get around the corner. I have to draw something that is perfectly symmetrical around this vertex here. Right, because there's my vertex, place where it turned around. This dot is 2 squares on that side, so it'll be 2 squares on that side. And if you want to convince yourself of the numbers, this dot here is at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's at -15. If I dropped another 4 here to continue the blue line, I would be at -19. That place there is 4 on the x-axis, so I should have to add 16 to this, because that's the appropriate number in my perfect squares. That gives me a total of -3. And if you look where this dot is, 1, 2, 3, it's at -3 on the y. Okay, but what happens from there? I've lost my blue line on this side, so I'm going to try and build it on that side. From my start point, go to the next x value. Well, that's here. I am one step away from the y-axis, so I need my first perfect square number sequence. So on it, I go up 0. Here, I go up 1. Here, I go up 4. 1, 2, 3, somewhere around there. Now again, these things need to be symmetrical, so this dot needs a partner here, and this dot needs a partner here-ish, so I can get this thing drawn in with lots of points. That's not too bad. So again, I've drawn another parabola. In fact, as soon as you tack an x squared onto a line, it's going to generate this thing. Now, something else I would like to point out to you. I'm going to go to the vertex of this parabola, and I'm just going to draw a line like this. So it looks like the parabola is resting on the ground. Just because I'm going to count up from this line to the parabola and see what I get. So the vertex, for example, is 0 squares above that line. This dot is 1 square above that line. This dot is 1, 2, 3, 4 squares above that line. You see the pattern happening? This dot is 1, 2, 3, 4, 5, 6, 7, 8, 9 squares above that line. If I were to go to the next one, which I can't actually see on my grid, it would be up 16. The next one would be up 25. I'm just going up by these perfect squares, because the perfect square in this equation is what generates the shape. So this pattern here is based entirely on these numbers. Why those numbers? Because those numbers are x squared. 0 squared is 0, 1 squared is 1, 2 squared is 4, etc. And you can count this pattern either from the vertex, if you can find it, or you can count it from the line that's sort of sitting in the front of the equation. Either way will work. So I'm going to try an example with a negative, so you can see that. And then I'm going to try an example with a number in front, and we'll see how that goes. So I'm going to sketch this one exactly the same way as I did the others. I'll start with this number in front, y equals 5. So you find that, 1, 2, 3, 4, 5. Here's all the places where y equals 5. To that, I'm going to add 1 for every x. So I start here, where my x value is 0, so I don't go up or down from there. Take one step in x, add a 1. Take another step in x, add 1. Take another step in x, add 1. Take another step in x, add 1. Go the other way, take a step in x, pattern drops by 1. So I get this line like so. All right, so we're going to finish by taking that blue line I just drew, right? That is that blue line. And from it, I'm going to subtract these x squareds. So, starting at 0, that's my first x squared. I take nothing away from this blue line. 1 dot over, I have to take 1 away from this blue line. Over, I have to take 4 off of it. 1, 2, 3, 4. Next step, I have to take off 9. 1, 2, 4, 5, 6, 7, 8, 9. Next step over, I have to take off 16. 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The next one I would have to take off 25, and that's going to put me off my grid, so I can stop. Going the other way, start at 0 on the y-axis, so neither up nor down. One step in, I have to take off 1. Again, subtracting because this equation has subtracting. Next step over, take off 4. 1, 2, 3, 4. Next step over, take off 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you see, there are those two symmetrical pairs starting to show up. Now, this one's a bit funny. It didn't generate a vertex in a clean place, but I can see it's got to be about there somewhere. So I've been able to generate this same shape of a parabola with a vertex based off this line, even if it's a subtraction. If you look at what happens, a plus x squared makes a parabola like that. A subtract x squared makes a parabola like that. So it's like a sunny face or a frowny face based on whether it's positive or a negative. So I'm going to clean this off, and we're going to try one that has a coefficient in front, and then I think you're ready to try the practice problems. So last example here, where I'm not just adding x squared to my line, I'm adding twice x squared to my line. So the first thing I should sort of do to get ready for that is look at my list of perfect squares and double them. Double them because this is a 2. So if I do that, 2x squared would be 2 times 0 is 0, 2 times 1 is 2, 2 times 4 is 8, 2 times 9 is 18, 2 times 16 is 32, and I'm going to be off the grid by the time I get to any of those bigger ones, so I can just stop there. Like all the other examples, I'm going to do the line first. So I start with y equals 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is here. Dash that across. It's y equals 10. And to that, I'm going to subtract 6 for every step in x. So no steps, I don't drop anywhere. One step, I drop 6. 1, 2, 3, 4, 5, 6. Next step, I drop another 6. 1, 2, 3, 4. Next step, I drop another 6. 1, 2, 3, 4, 6. Then I'm off the grid. And now I'm going to have to add these doubled x values, x squared values. So y is 10 minus 6x plus 2x squared. So no steps from the y-axis, I'm adding 0. I'm here. Next dot, I'm going to have to add 2. 1, 2. Next dot, I'm going to have to add 8. 1, 2, 3, 4, 5, 6, 7, 8. Next dot, I'm going to have to add 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And you see I've got those symmetrical pairs. So my vertex must be here somewhere. And there's my parabola. So putting a number in front didn't change the fact that it's a swoop down and a swoop back up. But if you notice, it did make it skinnier. Or I think technically it's made it taller, which just makes it look skinnier. So if you can sketch this, y equals a number, you know where that is, and you can add or subtract a certain number of steps every time you take a step in x, then you can make a parabola by adding either x squared or some multiple of x squared to that dashed line.